let me start the presentation, share the presentation with you, and then we can go from there. So let's put it on slide so you can view it in a much better manner then. Yes. So as usual, what we have done is we have collected your questions from the live session sheet as well as from the forum questions that we have already encountered, and we have arranged them in categories of topics. And according to those topics, we'll be answering most of the questions. I also anticipate that we'll be giving us some questions while the live session is on. We may take some of them if time permits. Otherwise, we always collect all of these questions and give the results in a supplementary kind of a presentation or document in your forum. So do not worry about them. We'll give all these answers to all the questions that you might have now or that you will have in the coming days. So first, let us see what are the questions that we have. There are a number of questions on schema and things like that. The first question that I am taking is from Gaurav. And the question is data abstraction and schema similar in terms of functionality, or there is a difference between them? Yes, Gaurav, the terms are very similar. Of course, they are similar, and we all know that that internal schema. There are three types of schema in a DBMS architecture: internal schema, conceptual schema, and external schema. We also know that the internal schema relates to the physical storage structure of the database, while the conceptual schema is the most used by programmers like us, which describes the structure of the whole database for the users, while external schema are used by users most often, and the user can see whatever they want to see, what they need to see, and the details are missed and not shown. Of course, we should remember the definition of data abstraction, which says that we have to give important information to someone without giving the details of that particular thing. For example, in programming language, data abstraction term appears a number of times. When we write a program, we say that there are in two-dimensional arrays. We said that there are records, there are struct variables, things like that. As you can easily understand that such types of complex organization of data is not available in the computer machine, in the microprocessor or the CPU, and therefore really they do not occur. But as far as the programmer is concerned, the view is different, and it is an abstraction we call, and this is a data abstraction in programming languages. So similarly, in this case, if we talk about schema and abstraction, we have similar situation. We have a customer table example in a customer information database, and the records of the customers may be described in terms of blocks of storage in memory, and these details are often hidden from the programmers. What the programmers see are probably information like tables, rows, columns, and at that level the programmers usually work. Now at the view schema, the users come in and they may not be aware of how the data is stored, whether they are in tables or not, things like that. Even the entire data may not be available to each one of them, right? So whatever is important to a particular type of user, only that much data will be allowed to be exposed to that particular user. That is a view schema. So of course, as we can see, there are levels of abstraction here. You can say physical abstraction, logical abstraction, view abstraction as well. And therefore, corresponding to every type of schema, we have an abstraction in place. So going forward, many questions were thrown on some basic concepts like table, like schema, like entity, even I think attributes, things like that. So yeah, attributes. So, and many of these terms are, I would say, are correlated with the word called schema. So first, let me again restate the ideas of tables, tuples, relation instance, relation schema, and then we'll find out why this confusion arises in the mind of the students. Now, relational data model, tables, or rather relational database, tables are the primary things. I mean, every information we store in terms of tables. These tables stores formally relations, but informally they stores information about entities plus the relationship among entities. And a table naturally has rows and columns. If you look at it, rows represents records and columns represent attributes. So for example, if it is a student table, the columns may be student name, student roll number, student's address, student's registration number, while every row would be these details for a particular student. Now comes relation instance. What is an instance? At a given point of time, if you look at a table, the content of the table will give you the instance at that point of time. Formally said, these records are tuples. So look at all these tuples that exist in the relational database at a particular instant. And that is the relation instance at that point of time. Now it is similar to the concept of class and object or class and instance in a programming language. We have a class and a number of objects in it. Similarly, the table column names define a particular table, describe a table. Just the column names describe the table structure. Now, when I fill up that table by adding rows after rows, then that becomes one particular instance or one particular object of that particular relation. Now, what is a relation schema? A relation schema describes the relation name. Basically, it's a table name, attributes, and the names of the attributes. So that's what they are. Now, why the confusion? The confusion is because of the following reasons. See, at DBMS, when we start reading, we first start with a relational data model, which is a mathematical kind of element. Now, in the relational data model, we talk about what relation, tuple, attribute, relation schema. Now, the moment you go to RDBMS, these terms are, I would say, occluded by the terms like table, row, column, like this. So, what is a relation in RDBMS? A table. What is a tuple in RDBMS? A row. What is an attribute in a RDBMS? Every column name is the attribute name. What is a relation schema? The same table again. So therefore, sometimes you will see that we use these terms synonymously without any problem. Now, even in schema, if I go about it, there are two types of schemas which are available. One is relation schema, which is nothing but a table. And there is a concept of database schema. Now, database schema is a set of relational schemas and a set of integrity constants. You understand that I have many tables, and the tables are connected, interconnected. And not only the tables are interconnected, there are referential integrity, there is a foreign key integrity, then the domain has an integrity, the domain from which the columns are taking their values, that has an integrity. So those many integrity constants plus the relational schema defines a database schema. So therefore, if I talk about RDBMS, then the definition of the table, definition of the field, definition of the relationship, definition of the views, definition of the trigger, definition of the procedures, these definitions are called a database schema. So now, I mean, when many times we jump from model to DBMS, at DBMS, we actually go back and forth between the relational data model and the relational database management system. So therefore, these terms occasionally are used interchangeably, but they come from different vocabulary. One thing I have not talked about in this particular slide, that is entity. Entity is primarily a word used in the domain of problem. The problem domain has entities. Now, for example, if you think about a paragraph and you find out the most important nouns that you have, they are the objects on which you work. So they will probably form an entity. But in RDBMS, an entity has a number of attributes. For example, I say student is something on which I use I have, I mean, that's an entity. The student will have definitely attributes like its name, roll number, etc., etc. So those are the attributes of an entity. Now, this entity will most probably be translated into a table in the relational database model, relational database management system. Point is, not necessarily every entity will be translated or transformed into one table. In many occasions, a one entity actually may be converted to more than one table, and then there are entities which have relationships. For example, if there is a teacher and there is a student and there is a relationship, therefore, which teacher teaches which students. So for this relation even, we might need to have another table, right? So find out from which vocabulary you are choosing the word, and then if you think about in this line, then you will always find out a correspondence between two terms, one used in at DBMS and the other one used in relational data model. Then this is also described more. For example, I have a department with, so department is the entity in the problem domain, and now it is a relation in a relational data model. And finally it is a table in relational database management system. Attributes were department name, building, budget, and they become therefore the column names in the RDBMS. Look at the tuple other than the heading to header. Look at the tuple like biology Watson 90,000. So biology department has a build in is probably placed in a building called Watson, and the particular department is maybe 90,000, whatever, euro, dollar, whatever. And then therefore these 5, 1, 2, 3, 4, 5, these 5 tuples are existing in this particular relation or table at this point of time, and therefore these 5 tuples constitute the relation instance at this point of time. Now, naturally, I can insert into it increasing the instance. I can delete some records, decreasing the instance. So, instance is a momentary is a momentary thing. It's a snapshot at a particular time, right? Change the time, the instance may change. But if you look at the structure of the department, like the column names and all, they will not change so easily, so frequently in our with every passing time. Now, then there were some questions about keys. Which attributes constitute keys? Then there are some confusions probably regarding super keys, candidate keys, primary keys, as well as some questions were there about compound key and composite key at some point of time. So we tried to cover them up in the next few slides. And let me check. I have changed a little here. I mean, this is not the exact perfect definition that you find out in the book. Let us assume that a relation, I mean, a table has a number of columns, so a relation has a number of attributes, and K be a set of some attributes of the relation. It may be all attributes, it may be a proper subset of those attributes. Now, question is, informally, does the the values of K, whether the values of K uniquely determine a tuple in an instance of that particular relation? If it does, then K is a super key. We'll have an example that will clarify things. Now, when I call it a super key, something is super here. So then our question is, maybe K has 5 attributes. Is it possible that we can find out this phenomenon that they can uniquely determine any tuple in the instance R, but number of attributes in that K may be less than 5, maybe 3. So can I minimize that the cardinality of that particular K, which is a set? So if I can do that, then I can ultimately make K a minimal set. If K is a minimal set, then K is a candidate. You may have many candidate keys. You can choose one of them as a primary key. There is no particular rule in that, but maybe problem domain will tell you which rule you should use and which rule you can use. Let us take an example which will clarify things. See, it is a student table with 3 columns: name, roll, marks. Look at the instance. if you look at the instance, then you can find out if I mean, I can say that if by name I can identify a tuple. Why? Because if the name is John, then there is no other tuple in this particular table, no other row in this particular table where John occurs. Similarly, if I say Maya, there is no other record row in this table where Maya occurs. So I mean, if I say John, then if I say name is John, I come to a unique row of this particular table. So if I say Maya, I come to a unique student in this particular table. Again, if I say Rina, I can come to a unique row in this particular table. So what does it mean? That means name is an unique identifier of this table. Similar is the situation with role. If I say roll is 25, you cannot go to two different rows. If I say roll is 28, roll is 18, you cannot go to two different students in this particular rows in this particular table. So if you argue in this manner, you find out that a name may be a unique identifier of this table. Role may be a unique identifier of this table. But look at marks. If I say 100, marks is 100. Am I reaching to a single unique row in this table? No. If I say marks is 100, there are two rows where I jump to. One is for John, the other is for Maya. So marks is not a unique identifier for this table. So for this particular table, unique identifiers are name and row. The moment I say that, combine name and role. So I mean, if name is John and role is 25, do I have two tuples, two rows in this table? No, I have a unique row. So therefore, name role together is also is a unique identifier. Similarly, name marks together is also a unique identifier. Even role marks is also a combined unique identifier. Take three of them together, name, role, marks. That is also a unique identifier. One question was there, is it always true that if I take all the columns in a table, then that can become a super key? Yes, that can become a super key. If a super key exists. So if there is a super key, then naturally name, role, take all the attributes or all the column names of a particular table, they together will uniquely identify the rows, no doubt about that. If there is a key, then that has to happen. But a database may have duplicate entries that is not necessarily always disallowed. So in that case, the situation will not be the same. Otherwise, you can have that. Now, what is the difference between the super key and the candidate key? In this example, you can see that there are so many super keys, right? One of them is a candidate key. In fact, two of them are candidate keys. Now, why others are not candidate keys? My question is, why name role is not a candidate key? Because the cardinality of that set, name, role, is 2. And what is the cardinality of the set name? 1. Which is less? For name, it is less. So a candidate key must have the minimal number of attributes compared to the super key. Right? So the difference between a candidate key and super key is a candidate key is always a super key. That is first. And the second thing is number of elements or number of attributes in a candidate key will definitely be the minimum number of, the set with minimum number of attributes in a super key. Now, out of this name and role, these are the two candidate keys. Which key should be chosen for a primary key? Here, we do not have any algorithmic determiner. You can choose any one, either the name or the role. One would be primary key, the other would be alternate key or candidate key. Simple, right? So therefore, what we understand is if you things. One is every candidate key is also a super key. any super key is not a candidate key. The super key with minimal number of attributes will definitely be a candidate key. One of the candidate key will become a primary key. Which one we do not know. Anyone we can choose. Like we choose, in a coin toss, right? So any primary key is a candidate key. Any candidate key is a super key. Then comes composite key. In general, composite key is a term which can be understood from its name. In our earlier example, we have seen that the key consisted of only one attribute, like name or like role. Now, it is also possible that more than one attribute will constitute a key, and then it is called a composite key. So look at the example: subject, faculty, subfact, student. The subject faculty subject relation has only subject ID as the primary key, as the key. So therefore it is a single attribute key. It is not a composite key. Similarly, faculty relation has faculty ID. Faculty ID is not a is a single attribute, and therefore it is not a composite key. Look at the student. Student underscore name, student underscore email, they taken together become a key. Understandably, if I say student name is Ranjan, there may be many Ranjans, but the email and the name together will constitute a key, a unique identifier. So therefore, student name and student email together become a key, and therefore it is a composite. Now there is one more concept called compound key. Now in a compound key, individual attributes also act as primary key in other tables. Like for example, the subfact subject ID, faculty ID. In subfact table or relation, subject ID and faculty ID are two different attributes which together become a compound key, become a composite key. Now, if I look at subject ID, this is a key in the relation subject. And if I look at faculty ID, this is a key in the relation faculty. Now, when that happens in a composite key, then we call it a compound key. So a compound key is essentially a composite key, but the components of the compound key themselves are keys in different tables. So we call them compound key, as if two different keys connected together, like two elements combined to give a compound. Similarly, two primary keys combined together to give a key in another table. So something like that. So therefore, it is a compound key. Now there is one more concept called surrogate key, which is of interest to many of you. Now you'll find out that in certain situations we identify the records by an artificial key. Now, for example, I have students joining in a queue, or people joining in a queue. Now the time of joining, which is not essentially coming from the problem domain, may become the timestamp when the person has joined the queue. Like for example, where many of you are filling up a Google form, the timestamp when you are filling it up, I want to use that as my primary key. So it is not internal to the entity. The entity does not have it. The entity has a number of different attributes. Like for a student, it has name, roll number, marks, etc. But when you join the queue is important to me, and that becomes my primary key. So it is a unique number, and it is not a natural primary key. Natural primary key is one where the attribute is inherent to the entity. This is not inherent to the entity. And I want to make this a surrogate, make this a key. I mean, auto-generated key, we can also say. I have a counter, I go on incrementing it every time some entity is inserted, and therefore it becomes unique, and I use that as a key. So that's a surrogate key. Now, you naturally may ask me, what is the need for it? The need for it comes, look at the second one, that is the most important. It has a primary key, but the primary key is very long. If it is too long, then the primary key use in primary key has a certain usage in the organization of the data in the memory actually, in files. Like for example, it is used as an index so that you can reach that particular record very easily. Now, if it is very large, this primary key is very large. If you, let's say, 1,000 bytes long, then using that primary key as an index is a very difficult proposition, and we cannot use that. So in that case, we use an external surrogate key. Sometimes the primary key that we think that that they should have, the values of this primary keys might change over time. For example, I may say first name and last name may become maybe the primary key, but for the same person, maybe last name changes after marriage. Then F name and L name cannot be used, as a primary key. So we need to import something like that. So something like surrogate key. So we'll do that. We do that. So these are all about keys, I guess. The concepts for keys are more or less covered. And also, let me tell you that these are some concepts which we typically cover in every year, in every run of this particular course. So they are common questions and frequently asked questions as well. So if you do not understand even now, if you have some problems, then do not hesitate to ask us in the forum, where we'll give you more examples and you can actually educate you a little more, because the time constraint will not be there at that point of time. Let us go to some other question, where the questions was about foreign key and references. So let us discuss about the foreign key and integrity that the foreign key demands, and then we'll talk about this. Now, many times we have two relations, and these relations have a constraint. So if we have two relations, one would be referencing relation, and the other would be referenced relation. Now, the referencing relation have attributes which we call foreign key attributes, and these attributes also do exist as primary key attributes in the other relation, in the reference relation R2. We'll have examples, don't worry. Now, if I look at a tuple in R1, it will be referring to a tuple in R2. So that happens only when T1, the foreign key component of the T1 is the same as the primary key component of the T2. That has to happen. So this is very, very important. Now let us see an example. Say that we have two tables. One is customer table, where customer ID is there, first name is there, last name is there. And the other one is contact table, where customer ID is there, contact information, something like phone number, email address is there, and the contact type. Is it work contact, or is it mobile contact, or is it home contact, is it email contact? Those types are written in the third column. Now, customer ID in the contact table must match with the customer ID, some customer ID in the customer table. That has to happen. Like for example, if I say 101 customer has a contact 555-2653 as a home work phone number maybe. Now we must have a customer called customer 101 with some first name and the last name. So this is the constraint. In this example, if you look at the customer IDs, there is no customer ID in this table contact which is beyond 101 and 105. So you do not have any customer ID with 99 in the contact. Neither you have a customer ID in the contact which is 106. Because the moment you put a customer ID in the contact table, that customer ID must exist in the customer table. Right? So customer is the referenced relation and contact is the referencing relation. Referencing relation must have one attribute that is common, not in name, that is common semantically to the reference table attribute. In this case, the name is also the same, custite. It is not necessary to have the same name for that particular column. But the values in the referencing relation must be one, which also exists in the reference relation for that particular attribute. I cannot write something else. I mean, we have one more example which illustrates this. Look at this. Department has a primary key, department number, which is like 10, 20, things like that. So employee maybe with employee name King has an employee number 7839, and he works in the department which is accounting, which is 10. So department number in employee refers to the department number of the department table. So which is the foreign key? Department number in the employee is the foreign key. What is being referred to? Department number attribute of the department table. Now I insert one more row in this employee table. Assume Ford is an employee that I want to insert into the employee table, who is a manager and who may be working in a department number 9. Does department number 9 exist? No, because I am only seeing 10 and 20, no 9. Therefore, the department with the department number 9 does not exist in the table, in the department table. And therefore, this is invalid. I cannot do that. If I want to do that, what I need to do? I first have to insert a row in the department table with department number 9. Only after that insertion, I can insert Ford working in department number 9. Otherwise, I cannot. But what I could do, I could insert Ford as a manager. I kept the department number blank, null, assuming I will put the value once that particular department is already inserted in the referred table, which is department. So I can keep it null. That much I can do. But if I keep it null, I must understand that then this department number must not be a key in the employee table, must not form a key in the employee table. If it forms a key in the employee table, I cannot keep that key as a null value. So if I want to do this trick, then this trick will only happen if the foreign key of the employee table is not also a part of the primary key in the same employee table. That cannot happen. So the idea that I talked about is actually formally written in this statement. The statement says exactly what I told you through the example, right? So if you want to have a foreign key referring to a primary key in the reference table, the value of the foreign key must be existing primary key value in the reference table, or it can be a null. But if it is null, it cannot be a part of the referencing relations primary key. It cannot be a part of that. So this is the constraint that has to be maintained by the foreign key. I do not think that anything else is required, but the question was a bit different. Let me go back to the question. The question was asked using MariaDB as the tool, and MariaDB has the concept of foreign key as I think the person. I mean, who is the person actually? Whoever. The question who asked me this question. The second part of the question is basically using foreign key construct of MariaDB. And the first part is about some references which does not exist in ANSI SQL. Maybe it is a specific thing in MariaDB and therefore it allows that. But the moment you say that it is a foreign key, even MariaDB cannot allow that, because the ANSI SQL interpretation of a foreign key is whatever exactly I described to you in the slides. So you basically need to worry about the foreign key only, and the foreign key that I discussed in this lecture, and not other things that probably MariaDB additionally supports and gives you. So you also asked about what are the other constraints that you may see. So I think that on delete cascade, even on insert cascade is there, right? Right? I mean, I think there is an on insert cascade also. So these are the different types of constants that you have to take care of, other than the references that you talked about. I mean, you can also say on delete cascade like that, and if you delete in the parent table, the deletions of the dependent rows in the child table will be, I think, automatically done if you do that on delete cascade. It will be automatically done. So these constants you can apply. Next question was an example from multi-valued dependency, which is a little, I would say, tricky. And the treatment that I see this in this example is absolutely right, absolutely fine as far as formal description of MVD is concerned. But maybe it's not. It's a little cryptic if it is not explained in later slides or later examples. Let me, I'll put up some more examples and some more slides for this in forum. I mean, in our publicly to you, so that you all of you can understand it a little better. Actually, whenever I talk of multiple dependency, three attributes come in. Contrast it with functional dependency. When I say functional dependency, two attributes come in our mind, X and Y. X functionally determines Y. But when I say multiple dependency, then three attributes come to my mind, right? One, maybe I may say, I mean, in this example, if I talk about, one is Y, the other two are Z and W. Three attributes, Y, Z, W. Now, in this, Z and W are somewhat independent, but ZW together determines Y, in a sense. This example also, child name, phone number, is not the best example that I can think about. Think about another example. Maybe it's also a very popular example. Maybe three columns. One is model number of a car. The second one, manufacturing year. And the third one, color of the car. Now, manufacturing year and color of the car are two different attributes which are not dependent, which are independent, right? I mean, if I manufacture a car in 2005, its color could be white, its color could be green. Similarly, if I manufacture a car in 2009, its color could be white, its color could be brown, its color could be green. So color and manufacturing year are apparently not dependent on each other. But car number, sorry, model, let's say it's a simple Zen car. Now Zen car, maybe Zen car manufactured in 2005 had white color. The same Zen car in 2006 manufactured has a green color. If these two rows are there in car table, then two more rows must be present in the car table. One is Gen 2006 white, and the other one is Gen 2005 green. So multi-valued dependencies are called tuple generating dependencies. So they say that if these tuples are there, some more tuples must be there. Unlike functional dependencies, it says some tuples are to be there in a particular MVD. And therefore, in some sense, it basically gives me a full constraint of the database, a little more than what functional dependency gives me, right? So a little complex as far as the concept is concerned, and the role and the laws, the rules of MVDs are also involved in naturally in these cases, and therefore, we do not much use this nowadays, but of course, as a concept, this is interesting and this is important. We'll put up some slides in the common press. Yeah. So in join, we had some questions from join, natural join, outer join, and left join, left outer join, right outer join, full outer join, natural join, equi join. Now let us just say natural join and equijoin. Both of them are almost the same, right? I mean, if I look at it, only I think the columns are more in equijoin, where I mean, after all, uh, uh, any join is is a subset of the multiplication of the cross product of two relations, right? I mean, loan cost borrower is the mother, and in which loan number is the common attribute in this case. Loan number equal to borrower number. I mean, loan number in loan is equal to loan number in borrower. Those tuples will come in join, be it equijoin, be it natural join. But in natural join, we have the common attributes. Which are the common attributes? They appear only once. That's in natural join. Whereas in equijoin, the common attribute occur twice, as if they occur once for the left relation and once for the right relation. Right? So that is the difference between natural join and equijoin. The question was on natural join and equijoin only, as far as I remember. The outer joins were not asked, right? So that is one. And the next question that I will take right now is this uh, um, this relation. If you look at, there are some examples where relational algebra and SQL query, they were taken together. I mean, they're shown together, and we probably wanted a little more explanation on that. And if you look at these two tables, look at them a little. You see that in our furniture details, there is a furniture ID like BRD1 and the color brown. And BRD1 fits in a living room, bedroom, whereas sofa, which is DR02 fits in a drawing room, which is given to me in the first table, left table. Left table says if the ID is DR02, it fits in drawing room. If the ID is SR1, it fits in a study room. If the ID is GD3, it fits in a garden. And it's, I mean, in the right table, it says if it is a computer table, it is SR1. If it is a computer chair, it is SR1. So this information is given to me in the right table. The question to me is select the furniture type of all furniture with color brown. So what I can do, I can simply do a product of these two tables and then choose the tuples with the color brown, because furniture type is not available in the right table. Now color brown is not available in the left table. So I need to have either a join or a cross or a product. So I may choose in the first example I have chosen a product. So you see from left to right to left in the relational algebra, from right to left. What I first do, furniture placement cross furniture details. So in that particular product, I select, what am I selecting? I'm selecting the left table's ID is equal to the right table's ID, and the color is brown. So I do that. Once I do that, then I'm not interested in the color. I am only interested in the furniture type. So I take a projection on the furniture type. So when you look at a relational algebra and want to find out what it does, read it from right to left, not from left to right. Read it from right to left. Similarly, if you read a SQL, you primarily read the select statement first and check whether it's a cross or a join. Now it is a select something from A comma B. The moment I write A comma B, it is A cross B, product of A cross B. Now, what am I selecting? I'm selecting color is brown and furniture placement first table's FTID is equal to second table's FTID. So that's the selection clause, where clause. I select using that clause from where? From the cross product, from the product of these two, of these two tables. So that's how they match. I hope I'm clear now. And we can go to another one. The same one, a better one would be make a join. Why it is better? Because the number of rows that I come to in this case is 5 after join, while in the cross product it was 35. So my maybe my query becomes a little more faster, a little more efficient. So that's what it is. I have a little more time, so I'll have one more example. This is a very nice example where a rename operator is essential, is needed. Simple table, ID is there, place is there, price is there. I want to know the places where price of this furniture with FID 1 is more than the price in Kolkata. What are the FID 1? Kolkata, Noida, Ahmedabad, Delhi. What is Kolkata price? 20,000. What is Noida price? 35,000. Ahmedabad price? 12,000. Delhi price? 25,000. So the answer to this question would be, Noida and Delhi. That's the answer. But how do I do that? I could easily do that if I do a cross product of this table with this table. Make a cross product of this table with this table itself. And then select only those FIDs which are 1 and the ones where the price of the left table of the right table is more than the price in the left table for Kolkata. If you do that. But first point is I need to multiply the same table, one table with the same table. How do I do that? I cannot write A, comma A. I have to, therefore I need the same table in 2 different names. Because later I need to compare. If I have 2 tables with the same name, then when I compare when I write the select clause, I cannot refer to them easily. Look at this. I first do the cross. I first rename the table as row, as rel 1. The second table, I rename it as rel 2. Then I do a cross. And after that I say, in the left table, look at FID 1 and the place Kolkata. And in the second table, now we compare the first table and the second table. The first tables, the left table's ID has to be the same as right table's ID, and the first time's price has to be less than the second table's price. Now, if I did not rename them, then this sigma clause, then this select clause, the where clause in select, I could not write it. Both of them would become furniture underscore price dot FID, furniture underscore price dot FID. So I could not distinguish between the 2 tables which I actually made a product of. So to distinguish these 2 tables, I had to say that let us say that left table is rel 1 and let us say the right table is rel 2. Although these 2 tables are the same and the instance of them at this point of time are the same 2. But this was essential because without them, the sigma in the relational algebra and the where clause in the SQL query would not be written. Right? So therefore, we had to do this thing. Now, last question that I will take today is redundancy. What is redundancy and what is normalization? Now, redundancy, as the name suggests, the same data is repeated in the same database multiple times. Now, if you look at this this table, you see that the department name, department number, department name, and department manager will be duplicated for every employee who works in the department. Like for example, Deepak works in 10, department number 10. And what is department number 10? 10 marketing. And what is the manager? Ankit. If I have one more row with department number 10, maybe Mira also works in department department number 10. Then the same department name and the same department manager has to be stored there. Now, if I had 100 employees working in department number 20, then 100 such rows had to be written in which 100 times department number and department manager would have to be specified. So this is the redundancy. And redundancy leads to 3 types of anomalies: update anomaly, insert anomaly, and delete anomaly. And to eliminate these anomalies, we use normalization, right? Now, assume that I want to insert a project, but the project does not have any employee as of now. Now, if I go here, I cannot, I'm in a department. It's a department actually. I want to add department in a department. Is it department? I cannot insert a department unless the employee, unless and until an employee is assigned to that particular department. I think that's what it's not project, it's department. Now, maybe I want to do that. Then, if the moment the employee name, employee ID, and employee names are not known to me, I cannot insert that particular department. If maybe this particular table has employee ID as the primary key, so I cannot keep that particular key as null, and therefore I cannot insert a new department unless the department has an employee in it. Now, similarly, if I delete a department like 20, then I need to delete. I will be deleting all the employees who works in that particular department. And if some employee who works in the department and doesn't work in another department, then maybe that employee details is lost by the deletion forever. We do not have that particular employee anymore. So we do normalization to minimize this redundancy and remove this insert, update, and delete anomaly. Now, we have a question right now, how to find the highest normal form of a table. Now, this tells you, I mean, in a very nutshell, what is to be done. You have to find out that it is in 1NF. Now, if the the contents of the column are not multi-valued, it is in 1NF. So to check it is 1NF is very simple. Each cell in the table must have only one value. It cannot have two values in any cell. Then it is 1NF. Now remove partial dependencies from 1NF, you will go to 2NF. Remove transitive dependencies in 2NF, you will go to 3NF. And from 3NF, you go to Boyce code normal form by making, I mean, they're competitive, I mean, they're kind of, at the same level. Maybe in BCNF, what you need to do is the left-hand side of the functional dependency must be a part of the key. And 4NF we do not use much, but we go up to 3NF. And 3NF has something to do with MVD, multi-value dependencies as well. We do not go to that. So you have to do these steps algorithmically to go to 3NF. So that is the, if you want to check whether highest normal, what is the normal form, then you have to find out whether the functional, look at the functional dependencies and find out whether there are partial dependencies. If there are partial dependencies, it is in 1NF. Now check whether there are, I mean, be sure that it does not have partial dependency. Then you check whether transitive dependencies are there. Then you remove transitive dependence. I mean, then it is in 2NF. Assume it does not have partial dependency as well as transitive dependency, it is in 3NF. Right? So that's how we find out. And then you find out whether the left-hand side of the functional dependencies are the keys or not. That will tell you whether it is BCNF or not. So I have to stop here because of the time constraint. Let me stop sharing this document now. And I think it is time, and I hope that I clarified some of your doubts. You are always welcome to post your questions in the forum, and I will explain it a lot in more detail. If you so wish, we could probably meet in some other way to some of you. If you really need that help, you can do that as well. Not in a live session, but generally, if something bugs you and you cannot go into that, you cannot understand that. So I think with that, I conclude this live session now. We have one more live session at 6 o'clock, I think. So should I, so let me close this live session with good wishes to you, and so that's all for today's live session. Thank you very much. Thank you.